Yeah.
Shall we just,
Yeah. It should be.
I don't think it's working.
So just yeah, now.
All right, so let's start. So I'll start with trying to explain what is it that I would like to do, and you will have to decide whether it's actually of interest to you or not, because it's quite technical, and also you will have to do a lot of the work yourself. And I'll try to guide you. So just yeah, so you know exactly what you're going into. Uh, so super resolution is generally considered, as we discussed yesterday, quite complicated model, with a lot of nuances and a lot of technical details. But what I wanted to show you, try that it's actually today it's very easy to start with. If it's something that is of interest to you, it's really easy to start. And then the second point is that this is how all of these models work. So most of us are practitioners and users of AI models, but it's actually, it sounds like crossing this boundary between being just a user of ChatGPT to actually train your own model. It sounds quite intimidating, but I just want whoever is willing to try, you get a feeling that it's actually crossing this boundary is today incredibly easy. And then it opens the whole range of possibilities what you can actually do beyond just using ChatGPT, right? So I've sent to you to the WhatsApp what is called the Google Colab notebook. So any of you who had a chance to open it, it's basically how many of you are familiar with Python notebooks? Okay, so, fantastic. Okay, so that's what we are going to use. It's a remarkably straightforward and user-friendly computing framework. Basically it's like Lego, right? You have all the components there. You just need to put them together. There are endless possibilities. And so this notebook already contains pretty much all of the steps. But obviously, going through the steps will take you 3 minutes, right? But the question is whether we can dig a little bit deeper and try to, yes.
What runtime type do you use?
This is Python 3.12.
Yeah, but there are different runtime types for.
With GPU, without GPU.
Yeah,
with
memory.
T4. Yes, that's a very good point. Thank you. So you need to switch to T4, which is a basic GPU runtime. Fantastic. Yeah. It's a very good point. Yeah. So these are available for free. So you shouldn't have any difficulty to get them. If you have run into any issues, let me know. And so so there are I will just step by step explain what this notebook is doing. So the first, we just install some preliminaries. You just do Shift Enter and you run each cell in order. So you can you run this first cell, you install everything. Then I just put a bunch of kind of milestone and instructions depending. We have limited time, and obviously there's no objective here to achieve any production anything. We just want to familiarize ourselves with how this is structured, how it works. And then in case any of you is interested, there's endless possibilities to dig deeper, and we can have a longer project. There was this discussion that we can have we can continue to push further. So there are several milestones. First is something very basic. You get a little bit of basic data. We discussed this yesterday. There's this fantastic Sentinel-2 naive matched data set where you have both high resolution and low resolution data. This is the hardest part. They've done everything for you already. So all the data is there. You choose certain amount of data that you want. You download it locally. You prepare the data. Again, most of machine learning is about data engineering. It's very little about training. It's a lot of data engineering and distillation, preparation of the data. So you need to prepare the data. Again, you have already the scripts to do it, but you can play with them a little bit. You organize the data in the exact format that the model expects for training. You create these training data sets. Then you can configure your network. There are lots and lots of different options, different parameters, different, yes.
I have only training and validation, not the third data set.
You can do everything with just one data set. For the sake of this experiment, right? Obviously, for real, right? You will need training data set, you will need validation data set, and then you will need separate testing data set. And in the configuration, you can split them between separate data sets. Mm-hmm. For this, in the code that I have in the notebook, I have everything together because we don't try here to develop a production model. We just want to show that it actually works. The model trains and it actually knows how to recover information. It's a toy example, right? Mm-hmm. But in reality, of course, you will need training, you will need validation, and you will need testing.
You always can like take a part of trained data set, remove results, and use it as test, right?
That's exactly what example does. Yeah, but it's I mean that's I think from the logical point of view probably it's a mistake. I just wanted to simplify just to have because dealing with a lot of data is already takes a lot of time, so I just wanted to keep it simple. And then as we go, once we realize this, we can go through additional levels of complexity, like in a game, different layers. So we want to actually, so if you train your model and you actually test it, you will see very quickly that it works, right? But it works because your data set is very small, you validate it on your training data, so it will work, but it's not a good model, right? So to make it a good model, you need to further adjust the data, you need to work with the data to accommodate with different statistical distributions of how your real world data will look like. And so you will need to add different levels of noise and distortions in your training data that will take into account how your real world data will look like. And then, so you can retrain, you can see the results, and then to make it even further, a little bit sophisticated. So when we start with the basic data, we just take high resolution data, we downscale it as was discussed yesterday. We downscale it, and then we have perfectly matching pairs of high resolution and low resolution data. However, this is not very realistic. What we actually want is to have low resolution data from Sentinel-2, from real satellite, and then high resolution data is a matching data from high resolution. So naive is actually, it's an airborne, it's a plane that flies and collects the data. And then finally, yeah, you want to do all sorts of more sophisticated normalization to make the matching of the low resolution and the ground truth pairs to match them better. So that's the plan. Now, these code snippets that are available, you have, I'm sure you have ChatGPT that is available that you can ask to modify this code. You can go through the steps very quickly. If you get stuck, let me know. But generally, you can run this code just cell after cell, and you will get training within a few minutes. So let's try to do this, and let me tell you whether what is the results that you are getting, and we'll take it from there. So I would say, I'm happy to take any questions. It's completely open to discussion, but if you want, please try to do this, and let's see how far we can get.
How much for this first step?
Once you start training, obviously the training itself takes time, right? So we don't want to waste this time on letting the model train for 4 hours. It's enough for, let's say, you get to the point when it's actually running, and then we wait maybe 5-10 minutes until it gets to some milestone. It actually it trains, it saves the weights, right? And then you can use these weights for the validation and for visualization. So let's give it 5-10 minutes to train, and then let's try to visualize the results. So what you have to be careful with is you don't want to run all of the, you can run all of the cells, but there are cells that are for different steps. So for example, there's a cell, this cell here is to generate Sentinel-2 naive pairs. So you don't want to run this cell at the moment. You want to run only the cell here that generates, you can see here at the top, naive to naive image pairs.
Mhm. Currently, we have only 3 channels, RGB, yes?
For now, we are working with RGB. Yes, yeah. It's a great question, but the model that we are using is it's a very flexible framework, but by default it's designed for RGB. So I didn't want to modify the framework itself too much. So for now, we're working with RGB.
There is some kind of bug there. It does not find file.
It does not find file. Can you
Elaborate?
yeah.
So yeah, it does not find the content data basic cybernetics for train queue.
So let's work through this.
In the last when the train script
So
runs.
I'm stopping my training. Yeah. In the last
cell, yeah, it doesn't find some kind of file and it crashes.
So as I said, this last step you actually don't need at the moment. You are running this step here, right? S2 plus naive, right? Is that correct?
Well, it's the same for me, but I don't run the cell application. But the data set generation took 0 seconds and finished.
So which cell are you talking about? You are talking about
the very last cell, like the Python train basic start train pipeline. So the train point.
the train pipeline you're on.
Yes, train of pipe. The very last cell.
Okay.
So this script doesn't run for me.
What is the? Let me come and see what they are.
Yeah.
Did not actually Because yeah.
Це не влаштовують, так навчання. Я думаю, або інтересу.
You know, yes, just go inside city or something. Slash.
So what should work?
Yes. That's okay. That's yeah. I did some change last week. Good catch. So I'll show you what you need to do. So yeah.
You have to add it to bits above because before the data generation, you download the data and you have to download it to the right place.
So yeah, exactly. So you need here in the second cell, you just need to add like this. And yeah, and you just rerun this cell.
Of course.
Okay, excellent.
Thank you.
So for those who managed to get it working, you will start seeing these numbers, and I'll try to explain what these numbers mean. So right now we have very little data. We have just a tiny data set, toy data set. And so you have some obviously information. You have this, what is, so you have iteration. So it's an iterative process, as we discussed yesterday. It's the stochastic process where it collects a subsample of available training data and it tries to fit a model on this data. So you would have epoch is just you break up the iterations in certain epochs. Then you have iterations, and then you have some, how long does it take? And then you have very important parameter here. And this parameter is called learning rate. And this basically means how much the model changes, updates the weights. So the model gets new data. I mean, for some of you probably know this very well. Maybe just for those who, just to explain what you are seeing, is that the model has a new example, right? And then this parameter tells the model, okay, you've seen this new example, you learn something, how much should you adjust your internal parameters? And so what you want is you want to start with relatively large learning rate. So initially you learn very quickly, but then this process is very noisy. But then once you start to converge, you kind of refine your learning more and more, and you want to gradually decrease this parameter. So the more you arrive at towards the solution, the more, this is what is called fine tuning. You reduce this learning rate, and so you arrive at very fine solution. And then finally, this last number is very important. This is the loss function, and you can have many of them, but in this case, there's a very simple loss function that just measures basically the distance between the predicted pixels and the real pixels. And what you ideally want to see is that this loss function decreases. And if it decreases, it can go a little bit up and down, but generally you want to see a trend where this loss function goes down. Okay, anybody observes the loss function going down? Yeah.
Yeah, but the learning rate is fixed. We have
So the learning rate is not fixed. There's a quite sophisticated algorithm that selects the learning rate. And there are different ways. So the learning rate actually looks at the loss function or the gradient of the loss function, and then it just dynamically adjusts accordingly. This is the thousands of papers that have been written just on this particular part. Is how do you adjust the learning rate, looking at the at how loss function changes.
I'm quite familiar with just the learning rate in reinforcement learning, where it is adjusted for LLMs in cycles, and it can go up and down to introduce more noise and then to optimize.
Yes.
So it not for it to not get stuck in the local minimum.
Exactly. Yeah.
But here we just make it smaller and smaller.
Yes. So in the previous step, you had this configuration file that you have just there's this step here, this cell, where we basically saved this configuration file. And this configuration file is there are lots of different parameters, and all of them are actually very important. So if you've seen that that it's actually your model is learning, the loss function is going down. The next good thing is actually to go through this configuration file, because this is a very generic thing. It's for all the different AI models, you will always have this configuration files where you actually decide all of these different what is called hyperparameters. So all the different algorithms that they use for the different parts of the model. So I'll give you just maybe a couple of minutes, but so we don't need to right now to converge to some very good result. Just tell me if it's the model is running for you. We can discuss the configuration file now. For everyone, it's working.
Yeah, but it doesn't go down consistently. It sometimes jumps in the top.
It's always like that. It always goes up and down. But if you would let it go, it would just very slowly, this very typical function that fluctuates, but eventually it converges. And this is exactly what
I have a question.
Yeah.
We see that validation matrix is PSNR. Can you
Yes.
just a little bit elaborate on it?
Yes.
What's the intuition behind it and how it works?
Yes. So this is what this is peak signal to noise ratio, right? And so this is a very simple quadratic function. It's mean square error essentially. Okay.
Oh.
Normalized to the peak signal. So in this case, the way that this particular model normalizes the images, you normalize everything to 1, right? So the peak is 1, okay? And then basically you calculate the mean square error. It's the most basic, simple.
Normalized means
yeah. So there is and actually the specific loss function that we are using, it's a good question, because part of all these different parameters are here in this configuration file. So for example,
you see the
yeah.
Adam optimizer.
So there are all the optimizer. There's different augmentation parameters. So let's quickly go line by line. So you just define basically you are calling your model super resolution model, whatever. Then you want to achieve a scale of the super resolution, which is 4. You want to use single GPU, which was what we have right now. Manual seed, you can start kind of from it's just a seed for randomization, and then we just generated these data sets. So we defined where the model can find the training data sets, and then so for example, this is here very important because it actually takes your data and then it's augmented. It adds additional data sets that were not necessarily in your data. There are many ways to do it. So these are very simple ways to augment with data. It's basically it's randomly flips them in different ways, horizontally, vertically, and so you have a richer training data set.
What is the GT size?
It's ground truth size. So it's the size of the actual ground truth tiles. Okay. So there are, again, for validation, where the different data sets are.
Can also, what is the maximum scale we can specify in the settings file?
Yeah, that's a great question. So you need to have, you cannot arbitrarily choose your scale because you have training data that would support certain upscaling factor, right? So in this case, we generated our data to have 4x scaling factor. So you can only choose 4.
Or up to 4?
It's I don't think it would be able to deal with, for example, because it doesn't have the training data set.
So in this particular case, because we generate our data, what the final model will be doing, its task is to reverse engineer our downsampling algorithm, so it can undo it or reverse it. So it is not like the true upscaling, but just figuring out what downscaling we use.
Pretty much, yes. Yeah, that's exactly what it does. Yeah.
Yeah. For example, for different models, for different training data sets, we can use different methods of generating data, and the model will not be applicable for any other methods because it's only trained on that one particular data set.
Precisely.
And it reverse engineers that particular method.
Exactly. However, there is still a very interesting point here. And the point is that this is obviously very naive, okay? And this is not a real world situation. However, if you take large tiles, okay, and then downscale it by a factor of 10, right? Intuitively, when you downscale, you lose enormous amount of information, right? You lose it. However, you can train your model to reconstruct the original tiles with nearly perfect quality. So this is not a real world scenario because in reality, your real images will not be perfectly downscaled from they will not. Yeah. So this is not something that will work on real satellite. But there is still something very interesting in this exercise because it's still, although intuitively you downscale, so imagine if you downscale by a factor of 10, you reduce the size of the file by a factor of 100.
Yeah, we could compare it, for example, with manual method, because if we were to do that by our hands, so that's a tricky and complicated problem to undo the unknown method they used on for downsampling data set, but the neural network can figure that out and restore it.
Yeah, so this already something very counterintuitive there that is a good thing to learn from. But again, this is just for experimental purposes. This will not work in real life. So I'm just going to finish this. The moving average decay and the optimization type. This is exactly the choice of the learning rate. Is a particular algorithm that chooses the learning rate depending on the dynamics of the loss function. And then there is a scheduler that kind of just manages the whole process. And then there are losses. So I want to stop a little bit on the section of the loss. There are there are dozens of different loss functions that you can use for particular purposes. And right now we are using this L1 loss metric, which is pretty much the simplest you can use. But in this framework, which is called basic super resolution, it's you can basically add and choose any collection of different losses. So it's this huge play field of how you can experiment and try different things. All right, so if that makes sense, and you would want to take it one step further, you can now run the cell that generates Sentinel-2 and naive pairs, and then you can try to run train on that. But for anybody that didn't finish, it doesn't need to finish, but it wants to save.
Currently, we are at the 4,000 iterations.
Yeah. So
model and training state saved.
So if it's saved, exactly, you can stop. You can just stop. And now, so I don't have a ready cell for it, but I would like to give you this as an exercise. You need to go on the basic SR GitHub page, and there's a precise description there. How do you run testing? How do you actually visualize the results? And so this, I want you to try to do yourself. So this should be pretty straightforward. You need to go to this link here. This is the link of basic SR, and you need to find instructions there of how to run and configure and run the testing to basically visualize the result. So take 5 minutes to try to do that.
We have to move to this markdown file.
Yeah. So what you want is yeah. So I'll give you a little bit of you want to. This is the how to explanation how to do testing. What you want to do is you want to start with the single GPU because we have a single GPU, and you want to take this YAML file. You want to open it in a side window in Colab, and you want to just direct it to your data, and that's all you need to do. And then you run this command, and you should get the result. So you need to point to your data, and you need to point to your model that you just saved.
Can I ask you a question about the data set that you originally used for your models?
Yes.
So here we have good quality images, we downscale them, and then we train our model on some method we use for like blurring, and then we have a quality images. But in real life, you have to have a real images from satellite, which is not the good quality, and we want to enhance them. And that's the question, how did you get better images than the original images from the satellite you get to train your models?
This is the absolute key, and this is exactly what we are going to do in the next step. Because in this S2 naive data set, they already did this. So they took the images from a satellite and they matched them to the images from a plane. So this is exactly this is really the big deal, because as was discussed several times day before yesterday and yesterday, data, this training data is everything. This is the most important thing. And what is happening right now, that there are more and more these training data sets that become available, right? So people share these data sets. And so this particular group, so on this called, this is from team called Allen AI, they actually collected data and they shared. So this is what makes it right now so straightforward, is you can actually have very carefully selected, matched real satellite to real airborne images.
Do you merge a few images from the plane to fit the scale of the satellite image? Like the
Absolutely. There's a lot of work that is going into making sure that they are perfectly aligned. So they are pixel to pixel aligned. And this is really complicated. There's a lot of steps involved in this. But again, in this case, they already did it for us, right? So this is what we want to do. The next stage is that we actually download these pairs and we want to train for real, if you like, right? So from real satellite to real ground truth, except that there are lots of nuances still. And to train a big model, you need a really very large volume. So we won't be able to train a real model on just T4, this one GPU. You need lots of GPUs, right? But this is as close as we can get to real case right now.
But there are also satellite images with good quality. They are usually paid, but why not to use them? But images from the plane, which are, I guess, also like paid to obtain.
It's a very good intuition, and have you been yesterday?
Yes.
So this yesterday, I was trying to make this point that
the satellite data is not perfect.
None of this data is perfect, and so this is the way to go. This is what I do. This is what everybody does, right? But it's not straightforward, because this data that was taken from very high quality, this is a commercial data at very high resolution, right? But depending on the angle that it's been taken, if you look, I think it's best you can see it here. So you see this building here, okay? This building here, because the image is taken from this angle,
Distortions
is
right.
it looks similar, but to the computer model, this distortion of dozens of pixels, right? It undermines the training process, because it's like with a child. I don't know, maybe you don't have this experience, but you try to teach something to a child, right? But if you each time that you teach them, you give them different instructions, okay, they don't learn, right? You need to be consistent. You need to give some consistent instructions, and this is precisely what is happening. you train this model, and on each sample you give different instructions, right? And so it doesn't manage to make sense out of it. So I'm not saying that it's just a part of it's just part of the challenge. It doesn't mean you don't do it. You still do it, and you use multiple stages of distillation of your data. This is what makes data science so hard, like really successful projects, because you need to make sure that the data is coherent. And this is by far this is what everybody is talking about. But you need to clean the data, and you spend 90% of your time cleaning the data, and then only 5% of your time actually training models. Because unless you did all of the cleaning, it doesn't converge, it doesn't make sense. So any progress with this, let me know. If you get stuck, so don't waste too much time, let me know. I'll try to advise. But, yeah. So just again to give you a lead, there's this options here. Options, and then testing directory, and then you can go to, let's say, the SSRGAN model, and this is the testing configuration file, and basically all you want is you want to change a few relevant parameters in this testing file to fit your data. So all you do is you change the path to your training data, and you change the path to your model, and it should work.
Which root directory do you have to select? The configuration?
This is for me, I couldn't understand.
Maybe it's AI.
It's AI.
AI decided that we.
No, maybe just somebody online that.
Well, this AI.
AI is spying on us.
Yeah.
And learning stuff critical ways to escape.
No one wants it. Maybe he just he couldn't stand all this stuff and just go out.
Yes, yeah, exactly, yeah. Because we only generated training data, so you put training, but you make sure that it's the same. The same part. No, you shouldn't be needing to create any folders or anything like this. You just tell the model where the your tested data is, and then you give it a pass to the weighting, the weights that we just generated.
Can you please show us the script for testing? How should we start it?
So this is unmodified. I mean the reason that I don't show you, I don't have it. I mean this is a it's yeah, I really wanted you to do it, but it's in principle all you need to do here is to change the path to your data, and to change the path that you need to do. You only have one test, okay? So all you need to do is you can delete this. You can just change the path to your data, and you change here the path to your model, and that's all you need to do. So that's the reason I kind of didn't. Here's the
Our test data can be any screenshot from the Google Map, right?
Sorry?
Our test data can be any screenshot we take from the Google Maps or.
Yeah. If you format it correctly, yes. So in this toy example, you basically you can use the exact same data that we just used for training, just as a just as an experiment. But in principle, absolutely yes. Yeah. So in principle, if you have sufficient amount of data and you train on it, you should be able to take any snapshot from the screen print from the Google Maps and run on that. Yes. But it needs to be at the right resolution. So it's it needs to have the dimensions. You actually can the dimensions don't matter. But if you want the performance to be really, it depends on your training data. If you want it to work on any resolutions, then you need to train on all resolutions.
You mean scale?
Yeah, meter per pixel, right? So let's call it altitude, right? So the scale, right? So you can train the model that would work on a range of different scales, but then you need to have training data that for different scales, and then it will work on different scales.
Yeah, if we train on the satellite dataset, we should not expect it to work for the photo from the drone. All right?
No, no. If you just train on satellite data of particular scale, it will be very unlikely to work on drone data. Yeah. So give me some feedback. Did you manage to, so if you change the path to your actual
Yes.
weights, okay, it worked. Okay.
Can you tell me the weight?
As well.
So it is experiments, model name, models, and there are some amount of models depending on how many networks you run.
Mhm. Thank you for your advice.
And once you generate it, you will have a folder with generated results, and if you double click on it, you will actually see the actual image.
Experiment.
So you should be able to see something like that.
Model. Model.
So there's a folder now with generated data somewhere?
Yes.
Where is it?
It's so actually this is something that you can set up in the configuration file, but it's just see what you have in the configuration. It should be there.
Okay. I just don't see anywhere in the configuration.
Okay, let me give. So you see, what you are going to get is you're going to get the same file names x4.
Okay. I see. Because I commented out test 2 and test 3. I thought we didn't need those.
Oh wait, okay, so you only test.
I only left test 1, so I have to add this file in the CMPL, right?
Yeah, but can you check your the low quality, the underscore LQ? Do you find it there?
Where should I find this?
Inside train slash LQ.
Yeah. But it was generated before inference, right? This data.
So you need to see a new file. Okay, let me. Okay, the only way I can solve this is just quickly do it.
We can relate.
Sorry?
We can relate.
And you have the same?
We had.
That's good.
We already got it.
You got the result?
Yeah, the result.
Okay.
The result.
Okay, fantastic.
How did you fix it?
How did you fix it?
Get results too.
No, I didn't.
You can find.
I didn't.
We can maybe help you.
Давай сюда.
No, I got it. Finish. Okay,
А з чому проблема?
Якого ерора?
А з чому проблема?
Просто не створюється, нічого не створюється. А це тебе оце створилося?
Де знайти?
Да.
Давай.
Де ви знайшли?
Кран термінал.
У мене проблем ніяких не буде. У мене просто не знаю.
Результат.
Тут basic.
Ви працювали. Треба
Did you add the configuration output? That's what you did?
Оце?
Це про візуалізацію.
Ніхуя.
І так,
А як ти поняв, що вона тут знаходиться?
ну ми шукали. А ну хто давно? Треба відкрити додатку.
Це типу змальований?
Так.
Що я таке розумієш?
Десь були ітерації.
Дуже мало ітерацій було до референтів. Треба було там в файлі 400 тисяч ітерацій.
Ну, але це тільки це. А, добре, з цього файлу. Тому що я тренувала на цьому.
Results. Okay, results.
Це непогано. Я тренувала на функціоналі.
Ну, я...
Там у нас train equals test. У нас ми тренуємо.
Okay, I got it. Yeah, it's right.
Просто в мене модель тренувалась цю штуку.
Ну, це все інша справа, коротше. Ну,
Добре, дякую. А як ви поняли? Що воно?
Okay, so
Punch.
this is the result. You got it? So if you so you can see that the result is pretty much identical with the original.
Yeah.
Now this is good, but it doesn't mean anything, right? Because we had a very small training data set, and
few iterations.
yeah, and so, but I mean, it's a balance between how much data you have and how much time do you give it to train, right? So this is just a validation that the entire system, the entire process works, but it doesn't really. This is not a real world experiment, right? But it's just a validation. We have we now went through entire process of both training and inference from A to Z, right?
Yeah.
So we have a template for whatever we want to do as the next step. So what I want to do in the next step is to actually what we discussed is that we want to go instead of using completely synthetic data going from downscale data back to the ground truth, to actually use real Sentinel-2 as a source. So for that purpose, you need to run this last cell, data generation cell, that is called S2 to naive, then slightly reconfigure your configuration file and run it again, and then we will have the actual, closer to reality case.
Yes. So just download multiple files now.
So you can, I mean, this style is pretty boring. So you actually can go to this data set, and then you can switch to a tab called files and versions. And here, I mean, you have, there's enormous amount of data here. So you can choose a few tiles. You don't necessarily see them, but you can just take a few examples, so you can have a little bit richer data set. You can, if you like, you can re-download them, but you can also work directly with what you already downloaded, and then reconfigure change a little bit the configuration file and rerun the model. That's what we want to do. Is everyone is clear on what we are trying to do? Just to
I was wondering, can we use this to confirm results of our deep strikes?
For sure. I mean, this is what is being used all the time. So it's not necessarily by me, but this is what both intelligence and journalists that don't have access to the specialized military satellites, this is what they use. So this particular satellite is being used all the time for verifying all these different groups of centers that verify through publicly available data. That's what they do.
You need to do more trial because we have now this coffee break and you can talk. And also, did you consider to give a project on this or something? Maybe something.
So that was my. So this is what I said in the beginning. Is that it's entirely up to you. If anybody is interested in the subject and wants to continue to dig further, the only thing that I wanted to achieve with this workshop is to give you a complete A to Z kind of experience that it's not as scary as it looks. It's just to start with, it's much more complicated if you want to dig deeper. But just to start with, it's really easy to start, right? So the data is available, the code is available, the frameworks is available. It's to start with is as simple as just changing a few configuration files, right? So for anybody who is interested in the subject, I'm more than open to, we can make it a project, there are different frameworks that we can put together. So that's more or less all from me. If anybody wants to continue to experiment, if you have any questions, but that's was the purpose of this workshop was just to give you a taste of different tools.
Yeah, thank you.
What can you just suggest what new we have to discover or try?
Absolutely fantastic. Yeah. So this is let me give you a few ideas of really new, interesting things that you could do. Struggling with some things. So there's this GitHub where there's a guy that is basically collecting all kind of everything about super resolution. There are hundreds of different papers and code repositories and everything. And one of the methods that is really cutting bleeding edge in super resolution and in general in AI is, and it's been discussed yesterday, I think, is combining different modalities, right? So for example, combining satellite imaging with natural language.
Yeah,
okay.
this discussion.
And this is so this one particular, there are lots of papers, you can look through them, some of them are complicated, some of them are really straightforward. But what caught my attention recently, and I want to share with you, is, for example, this pure paper, which does exactly that. It combines, so it makes the reinterpretation of the image by the large language model, it builds it into the loss function, right? So instead of what we discussed, the simplest loss function you can do is just compare pixels, okay, the distance between pixels. However, much more sophisticated thing that you can do is to say, okay, take large language model and ask it to describe the image, and then compare the description of the image between the ground truth and the actual reconstruction, right? And this creates what is called symbolic loss function, where you don't want just to reconstruct the pixels, but you actually want to reconstruct the meaning of the image, right? So this is a very powerful new way of loss function. And but it's, so here in this, here is the paper, right? And in this column you have actual code. So for any of these models, you can take a code and plug it directly into this framework, and you can test it. So this is if you want to test something new, this is where you can go and start very quickly testing your stuff. But on the data side, the bottleneck still, you have this, you have all kind of networks, you have different, all kind of losses. It's all very interesting, and there's a lot of innovation there, but the bottleneck is always remains with the data. And so even though, as I've shown you, there's this data image pairs that are available, the difficulty is still making them match as best as possible, because they're far from perfect. And so there's a lot of research that is going into how do you make them match as best as possible.
So there is only pure and MMSR, but group articles for multimodality, yes?
I obviously didn't read all of them. You are just me trying to explore, and then so yeah, you can even take the address of this page, plug it into ChatGPT, and ask it to review the articles and kind of find the articles on a particular subject that you are interested in instead of reading them.
But to actually work with these models and experiment and improve them, we need a powerful hardware.
And do we have a data set?
So the data set is what I've shown you. Okay. So the data set you do have.
For multimodal.
From this Sentinel-2 naive. Yeah. So this model, this data set here, it's a very large data set that you can work with.
I'm sorry, I got the results. Could you please tell what the difference is with the big client between the first and the second one?
So first, what we've done is we took ground truth, right? And then we don't have any real data. We don't have a real satellite data. We take only ground truth, and then we rescale the ground truth to create a dummy, just a dummy low resolution data. So we don't use satellite data, we use a dummy data set that is created from the ground, right? So this is just as a toy example, right? It will not work in real world, right? The second thing that we've done is much more closer to the real use because you use a real satellite feed, and then you match it to the ground. How is your result looks like? Is it, okay, but this is but it's very easy to get a little bit over optimistic because the reason that it's so good because you have a very small frame of dates. It's only that's right. That's right. So some just this you cannot expect the same result in the real, but it's just it's just that it shows you that the whole process does work.
Satellite movement on not high because I would see maybe involved. We tested with clouds.
Most of what we do is testing is clouds. Clouds is a very big bottle, and I showed. Have you been using it?
Yes.
So most of our work right now is on actually mitigating clouds, but it's much more complicated because clouds are just super complicated. Okay, so for now, what you want to start with is you just find images without clouds, okay, and you focus on it. You can't deal with clouds.
Yeah, but it's also
so these images are multi-spectral. Right? So you have 10 spectral bands, and also you have 10 bits per channel. Right now you are using this simplified 8-bit version. So this is even 12 bits. But it's it just means that there's much more. The data is much richer than just the page.
Yes, but the base how also reach the data like black and white clouds. We can see when they are white and the ground are yellow, but it's not the case for black and white image.
So first of all, it's not magic. So the information needs to come from somewhere. So there's a lot of data that doesn't have the necessary information we construct, and there's not too much to do about it. The reason that why this works so well is because the original data is actually of very high quality and very efficient. This is what the model is supposed to do all the constructions. To answer your question, it really depends on the data. So if you show me the data, maybe I will be able to say more. But it really depends on. And sometimes you can't. Sometimes it's not.
But is this model applicable? It's not trained on general data. Is it applicable to channel to channel species?
It is definitely applicable to some extent, but the less channels you have, the less effective the model. But it's not black and white.
Yeah.
It's not that it will work to some extent, but how far you can push it really depends on the Thank you very much.
Yeah, about multimodal data sets. This S2 naive contains only images.
Yes.
But if you're talking about multimodal, maybe there is some already created data sets with text and images, for example.
There are several such data sets, and you can also produce your own data sets. There are multiple, you can just use things like directly ChatGPT. So for example,
generate description.
yeah. So what you can do, you can use ChatGPT API, right? You send ChatGPT an image and you ask it to describe it, right? And so you can generate this labeled data sets, and then you run it on all of your data. You generate all of these labels, and that's your training data, right? There are specialized remote sensing, satellite imaging, large language models. There are, for example, there are several of them, but I remember right now this Click. I can send you some links that specialize on this, that are supposed to do even better job than ChatGPT. Although it's questionable, because ChatGPT now, if you take ChatGPT 5, it's extremely good.
Okay, but what is the like scientific novelty then of our this investigation? This project. If we have already ChatGPT who can describe the image.
So I think there's some. You cannot. I don't think it's the right thing to expect right now to breakthrough, right? In science. I think that there's several stages that you need to go through. And I think these are very interesting, absolutely non-trivial problems that you can try to tackle before going something that is, revolutionary, bleeding edge.
But I think it has a lot of business application rather than in the scientific.
100%. So I would, if I may, I would actually focus on some of the applications. So the best thing that you can do is to find some real world scenario where you can find some deep knowledge of the use case, right? And then taking some of these methods and applying these models to some. So for example, you can fine tune any of these models to a particular geography and to a particular type of use case. For example, you can combine super resolution in training. You can fine tune super resolution model that would be very good in detecting field boundaries. This is a huge application, right? So you can very accurately, automatically delineate field boundaries. If you are talking about agriculture, then you can do the same thing in urban development. So you fine tune a super resolution model, but you fine tune it together with some applied loss function that is built for a particular application. I think this is the most interesting. I would say this is the most interesting of it. And then there is another direction that you can go with that is really bleeding edge if you want something really novel, is hyperspectral data. In hyperspectral data, you have, so in this case, what you've just done, these are 3 channels. Then in Sentinel-2, it's 10 channels. And hyperspectral data is 250 channels, right?
A single image.
Each pixel has 250 layers, right? And it allows you to essentially do imaging, what is called imaging spectroscopy.
It's like in space, for example.
This is what they use in space, exactly. So this allows you to analyze the chemical, biological properties of the material, and this is really the bleeding edge, and this is something that we absolutely could do. Yeah.
And we have such satellites and data available.
I can get you satellite imaging. Yeah. I can get so I have now very unique data sets from. They have a lab in Zurich where they have their own hyperspectral cameras, and now we have a special kind of relationship with Planet Labs, which is an American company. Yeah, and they have new hyperspectral satellites, and they are ready to provide data. So the super resolution for hyperspectral data. This is the most breakthrough thing that you can do. But there are another directions if you want to do something in us.
Okay.
I mean, I'm just telling you all the options. There is a if you want to do something with military applications, right? What just been mentioned, there are ways to so this is we are trying right now to go from 10 meter to 1 meter, right? But what you could do is to go from 1 meter to 10 centimeter, right? And then being able to detect objects, targets with real military applications.
Do we have that effect?
No. Sorry.
And go to break or you
You can continue. Yeah, absolutely. Yes, yeah, absolutely. Thank you.
Елементно, знаєш, що ми робили? У нас щойно знімали